Hello everyone, welcome back to PMAC1105. In this video, I will be talking about one of the very important function in college algebra. It is radical function. When I mention the term radical, I mean that it could be any root because radical is a general term for root function. And when we say radical function, it could be square root function, third root function, or any root. Okay, uh, and in this video we will be talking about the domain of those root function and how to find domain. And if we have time, we're gonna use transformation concept in the previous lecture to sketch radical function. Okay, so let's get started. So section 5.4. Okay, 5.4. Okay, radical function. Okay, so the first part of our lecture, I want to talk about the definition. What did that radical function look like? Okay, so as you know, let me switch to this color. Okay. Okay, as you know, any function is notated with f of x. Okay, so radical function, of course, also started with f of x equal to n root of x. Okay, so n is a positive integer. N is always greater than 0, and n is the integer, positive integer. Okay, this is mean positive integer. Okay, so n could be even integer, or it could be odd integer. So if n is even, let's see what it look like. So if n is even, for example, n equal to 2, 4, 6, 8, right? Then my function, one of the typical example of the radical function when n is even, is that the square root function. So we have example, we have f of x equal to square root of x. Okay, so if n equal 2. Okay, so this is one we call that second radical function, or we call it square root function. Square root function. Okay. And if n equal 4, okay, then we have a fourth radical function. Okay. So then we have fourth root function. Okay. So if and so on and so on, you can replace n with any even number here. The good thing is that the sketch, the graph, the sketch of all even root function is have the same shape. It probably changes a little bit, depends on the input value when you graph it, but the shape is kind of the same. Okay, so the shape of all even root function, the graph, the sketch. Let's talk about a sketch. The sketch of any even root function. Okay, any even root function will be something like this. Okay, so I'm going to put over here fx is even root function. So if we have a square root, 4th root, 6th root, 8th root, 10th root, the sketch of the graph, okay, the sketch of function of those functions will be something like this. Okay, so if it is something like this, we can define the domain easily, right? The domain will be from 0 to positive infinity. Okay, because we include a 0 here, because we can take even root of 0, any even root of 0. And the range, well, the range will be the same thing. It can also be from 0 to positive infinity. Okay, so that is the case when we have n is even. Okay, and what if n is odd? If n is odd, it means n will be 3, 5, okay, 3, 5, 7, 9, right? A typical symbol of n is odd is when n equals 3. So we have this is cube root function. If n equals 3, so this is called cube root function. Or sometimes we call that third radical function. Okay, remember when the first time you introduced to a radical, the n value we call the index, right? So if n equals 5, then we may call that the fifth root function or the fifth radical function. Okay, same thing. And the sketch of any odd root function will be something like this. So you have y here, you have x here. So it's going to be something like this. Well, of course, it's probably changed depends on the n value. You know, so the cubic function, the cube root function, and the third root and the fifth root function will be a little bit different, but the shape, the sketch, kind of the same thing. It will be something like this. All right, for any odd root function, odd root function. And from this sketch, I can get the domain. The domain over here will be from negative infinity to positive infinity, and show it the range. Okay, you can see that all value, all the point. If you pick a point, on the curve, okay, you can obtain the x value, and we can obtain the y value, no matter what point you pick on the curve. So that's why the domain range is from negative infinity to positive infinity. Well, actually, you already know how to find the domain range of the function. So for the domain, you look at the x, and for the range, you look at the y. Okay. All right. Or I can have something. Another example. So this is example 1. This is example 1. Another example I can have for the odd root function is this. Fifth root of 2x minus 1. Okay. So over here, the domain, again, the domain is also from negative infinity to positive infinity. Okay, same thing, because for the fifth root, we can take the fifth root of negative number 2. But for the square root, it will be different. So let me give you another example for even root. Okay, for example, I have fx equal to a sixth root of x plus 3. Okay, so this is the shape of this function will also be something similar to this. Okay, so this is the fx equal to square root of x, and fx equal to third root of x, the cube root of x is sometimes we call the parents function. Okay, this one, if we want to sketch, it's in detail, then we have to apply the transformation concept. Okay, maybe on the second part of our lecture today, I'm gonna have you to do that. Okay, so that's the definition of the radical function. On the second part, I want to go through how to find domain of the root function. Domain of root function. Well, in order to find domain, if you look at the graph, actually you can find domain. But if you don't have a graph, and if they give you a function and algebraically radical function, then you must be able to find the domain. Okay. For example, I want you to find domain of f of x equal to fourth root of 2x plus 3. We know that for second root, right? For second root, we cannot take the square root of negative number, but we still can take the square root of a positive number and 0, because square root of 0 is still 0. It means what? It means anything inside the radical, okay, we call the radicand, okay, of the even root, okay, always greater than equal to 0. So in order to do this, you just need to set up the radicand, which is 2x plus 3, is greater than equal to 0. Okay, then we're going to solve this inequality. Okay, after you solve this inequality, you can express it in the with interval notation. You see that? So this will be the domain of the fourth root. Okay, for the second root, you do the same. You set up the radicand greater than equal to 0. Okay. In the second example, I'm going to put the radical under the denominator. Domain of f of x equal to 1 over 6 root of x minus 1. As you know, we can only take even root or positive number or 0, right? However, because the root over here is under denominator, even though we can take root, the even root, the 6th root in this case, of 0. However, if we take 6th root over here of 0, okay, it turned out to be 0. And when it turned out to be 0, the 0 will be under denominator. And we know that we're not allowed to have 0 under denominator. Okay, so in order to find the domain of any root, of any even root, okay, we set up the radicand, which is everything inside the radical, greater than equal 0, right? But because this is under denominator, so we can only set it up. We can only set up greater than 0, okay, not equal, because we're not allowed to have 0 under denominator. So I'm going to solve for this. So have x greater than 1, and we can have the interval notation easily. Okay. Now I'm going to give you example and find the domain of the odd root. Example 3. Of any odd root function, find the domain of f of x of cube root of x 2x plus 3. Okay. For the cube root, you know that we can take cube root or odd root of positive number and negative number and include a 0 too. Now you want to try, you go ahead and put cube root of negative 5, it works. Cube root of 0 will work. cube root of 5 also work. So for any, okay, for any odd root, okay, we can take the value. Of any x. We can take. Let me for any odd root, we can evaluate. Okay, let me change a little bit. We can evaluate. Okay, the any odd root function. Okay, at any x value. Okay, so from this statement, it means what? It means the domain will be from negative infinity to positive. Because no matter what value will be to belonging to negative infinity to positive, you plug into the odd root function, you still can evaluate that. Okay, we don't have any value on the number line that we couldn't take with odd root function. Okay, so the domain always from negative infinity to positive infinity. Okay. However, what if I have the odd root function in the denominator? If I have something like this, okay, fifth root of x plus 1. Okay, usually, the domain will be negative infinity to positive infinity, right? However, because we're not allowed to have 0, so the domain of any odd root function in the denominator will be from negative infinity to 0. Okay, let me see, is 0 work or not? Oh, so be careful here. Not from at 0, I'm sorry. So we had to delete this. Because we have to find the value that makes the denominator equal 0. And that value will be negative 1, right? Because just think about it, if you have negative 1 here, negative 1 plus 1 equal to 0, then fifth root of 0 is 0, is undefined. So in order to find a value that make the fx function here undefined, we're gonna set the radicand equal to 0. Okay, I mean the radicand could be different from 0. I'm sorry. Then x plus 1 must be different. X over 1 must be different from negative 1. X could be different from negative 1. Then the domain will be what? The domain will be negative infinity to negative 1. Union with, because we're not allowed to use negative 1. Negative 1 plus 1 will be the fifth root of 0. 1 over 0 undefined. So you have from negative 1 to positive infinity. So the domain here means that for any value except for negative 1, we can evaluate the fx, including 0. Just think about it, if you have x equals 0, right? 0 plus 1 is 1. Fifth root of 1 is just 1. 1 over 1 is 1. So it's still good. Okay? Alright. So I can do on the third part. I think I'm gonna do some example how to use the transformation concept to sketch radical function. Okay, we're sketching. Okay, we're not graphing, because if we have to graph, we have to set up the value table. Okay, we have to pick the point correctly. Exactly, but over here we just sketch. Okay, we just sketch. All right. Example 1. What if I want to sketch? Something like this. fx equal to 4x plus 12. So we need to figure out how this function over here transform based on the original parent function. The parent's function will be what? So first of all, we have to recognize the parent's function. The parent's function over here will be fx equal to square root of x. And the graph of fx equal to square root of x will be something like this, right? Okay. It will be something like this. But right now, we don't want to sketch fx equal to square root of. We want to sketch fx equal to square root of 4x plus 12. So we want to know like how many units it transformed from the original function here. Okay, so how are we gonna do that? So you see over here that, remember, if we add a constant to x, right, then we have the function shifted to the left certain unit. Right? If we subtract a constant, okay, according to the transformation concept we already learned, then we know that it's going to shift it to the right by that constant. Okay, so you see over here, look like we have plus. Even though this one is going to shift it to the left. Okay, okay, reference to this graph right here. Reference to this sketch right here. So we're going to shift it to the left. Okay, but how many units? Okay, so in order to do so, in order to determine the number of value you should shift it to the left, you're going to set f for x plus 12 equal to 0, then x equal to -3. So you're going to shift it. You're going to shift 3 units to the left. So the parent's function will be shifted 3 units to the left. So it will be 1 unit, 2 unit, 3 unit here. So my new function, my new sketch, the sketch of fx equal to square root of 4x plus 12 will be something like this. It will be something like this. It's going to be something like this. There you go. Okay, it's kind of, I'm not going to say the parallel, but it's going to kind of, the shape is kind of the same, you see that? But instead of starting at 0, so we're going to start at a -3. Okay, we're going to start at -3. Alright, now let's do another example. Okay, now I have fx equal to cube root of negative ax plus a. Let's see how we're going to sketch this. We know the parent's function. First of all, determine the parent's function. The parent function will be what? Will be fx equal to cube root of x, right? And we know that this is going to be something like this. We know that it's going to be something like this. Okay. So this is the cube root of x. Okay, and let me change this. So this is square root of x. Alright, so how are we going to shift it? Okay. How are we going to shift this one? So you have to be careful over here. In front of the x over here is a negative number. So if I change a little bit, so I manipulate this function a little bit. So I'm going to have, I factor the negative out. I'm going to have a negative ax minus e, right? And the cube root of negative is just negative ax minus e. So the negative value in the front over here means what? It means that you're gonna flip the parents function over what? Over the y-axis, over the x-axis. I'm sorry, because it's negative. Okay, so you're gonna mirror this curve here over, okay, over the x-axis. Okay, over the x. Then how many units is moved? Well, in order to calculate, so we just go ahead solve this. So it's gonna move what? It's gonna move 1 unit to the right. So over here is 1. So over here will be 1. So look like that the sketch of this graph, okay, will be something like this. It will be something like this. So it's gonna move over here. So first of all, we're gonna I'm gonna have something like this. So it's gonna be something like that. Alright, so it's gonna go through. It's gonna go through this point right here, 1. Okay, I don't know where it's cut in right here. Okay, because this is just a sketch, so we don't know exactly the value on the y. Where's the green graph over here, the green sketch over here cutting? But we can calculate it if I want to. Okay, but we don't have to because we just need to sketch it. We just want to have the shape. Okay, for the original one, it's right over here, right? Cut at the origin. But for the green one, it's cutting. It intersects the x-axis at 1, and because of this, okay, because of this one, okay. So for this one, we have to manipulate a little bit, okay. We cannot just go ahead put negative ax plus 1 equal 0, negative x plus 8 equals 0. So we know that it's gonna be, well, even though that we're gonna set up negative ax plus 8 equal to 0, x equal 1, 2. But the thing that if we doing so, we just can shift it to the right 1 unit without reflecting that. The negative value over here tells us that we have to reflect the parents function about the x first. Then we shift it to the right 1 unit. Okay? Okay. I think that's all for radical function. Okay, that's all for section 5.4. So I'm going to stop over here. If you have any question, please let me know. Okay, I'll be see you next time on the next section. Bye bye.